Yes, you are online.
Recording in progress.
Yes,
So,
exactly.
okay, so thanks for giving me the opportunity to give a talk here. So I will, contrary to what Adam was talking about, I will be talking about something quite concrete, model theoretic stuff. So not much category theory, although category theory is behind one of the results, or the main result of the test. So, yeah, the title is Uncountable Homogeneous Structures. By homogeneous, I mean ultra. I will just erase the black. At the moment, I will use slides, but at some point. All right, so first of all, it is, should say, joint work in progress. Adam Bartosz and Milna Czemonia originally started working with Milna Czemonia from Paris, University of Paris, and about some very set theoretic constructions of uncountable homogeneous structures using some advanced set theoretic tools called morasses. They do not work well, unfortunately. So, okay, in principle, we were interested in the question how to construct uncountable structures with some homogeneity properties. Okay, so the first block should rather be called notation, not definition. So I try to be consistent with the notation from the previous talk. Script F will always denote a phrase class. No. Okay, so forget a little bit about this general stuff. Sorry for that, but now very concrete categories. Okay, so F is a class of finitely generated structures. And let's say the language is countable, so both structures are typically finite or countable. Could be infinite, but still countable. So, of course, all these examples like graphs, orderings, groups, finitely generated groups would be quite okay, except that it's not a phrase a class because there are continuum many isomorphic types. All upper axioms of the phrase class are fulfilled. Okay, sigma denotes the class of all unions of countable chains. Since it was not introduced, I have to say that the age of a class, the age of a structure, okay, the mathematical structure here in this talk is a first order structure, namely a set, endowed with some relations and possibly algebraic operations. If there are no, okay, so for the sets are structures. We have, for instance, one relation equality, no relations at all. Groups, semi-groups, Boolean algebras, and things like that. These are all structures, and the H is the class of all finitely generated substructures embeddable. You have to be careful about the notion of a substructure. So in algebra, it is clear. In relational languages, for instance, in graph theory, there is something like subgraph and induced subgraph. The subgraph is not a substructure. Induced subgraph is. Induced means that you select, you have some graph like this, maybe whatever, and induced subgraph is, for instance, you select those three. You have to choose those two edges. Huh? So the structure is such that the inclusion is really embedding. That's in both ways. Okay, I only need this F bar, all structures whose edges in the original F. So if we talk about graphs, for example, F would be the class of all finite graphs. Sigma F all countable graphs, and F bar arbitrary graphs. If we put some restrictions, like triangle-free graphs, no triangles inside, then the same, yeah? So another example of the phrase class. And then this new math PP, in Czech, this will always denote the phrase limit in the sense as before. So this is the unique up to isomorphic structure that is homogeneous, and its age is exactly F. So it can be described. We will translate these things from category theory, we'll get this. Because the phrase class is additionally hereditary. Did you mention it? No. So you see, a phrase class is a class of structures that has these properties like in the previous talk, amalgamation property, directedness, which is called joint embedding property, every two structures embedded into a single one, and moreover, countably many isomorphic types. Maybe let me just write quickly the shortcuts. Amalgamation property, which I don't need to explain. Joint embedding property means that you write equal to, say, you can always find some embedding into this F. Yeah? This follows from AP. Because then you can get it from amalgamations. And let's call it CMT. There was something like being countably dominated. But in the classical phrase theory, countably many isomorphic types. Sorry, I forgot this hereditary. This means you have any structure from your class script F. You take any structure that is embeddable into this one and is finitely generated. And this is again F. Yeah? This is it. So, for example, if you take all finite graphs, all finite connected graphs, this satisfies all these integers. So let's use this. By being homogeneous, I mean ultra-homogeneous. Every isomorphism between finitely generated substructures extends to an automorphism. Okay, so this is written. And here is this question I want to address. Well, fortunately, Adam was not talking about uncountable phrases, sequences, things like that. So that is why whatever I say will be something new, for some of you who don't know these things. Well, uncountable just means uncountable, yeah? Homogeneous, we repeat, every isomorphism between finitely generated substructures extends to an automorphism. So it means like the automorphism group is quite rich. All right, I should have written maybe, or I can just say that classical phrase theory. Let's say that this, what Roland Fraser was doing in the 50s, can be now called classical phrase theory. More than theoretic, he even didn't like algebraic operations. Structures were relational. But okay, later people realized that it's not necessary. So the theory includes finite homogeneous structures. They also do exist. A nice example is actually from projective geometry, the so-called Fano plane. You take all projective planes of degree at most 3. Now degree means that every line has at most 3 points, and every point belongs to at most 3 lines. This apparently has amalgamations. It's this thing. There are finitely many types. The Fano plane has 7 elements. Everything is fine, but you're reading about that. Okay. no, not always exists. The language is relation. So let's agree that we have our original phrase class is really infinite, yeah? It has arbitrarily large finite structures. Finite. Okay, so then there is still some nice example. I mean, I find it nice. On one hand, it is well known, should be well known, but on the other hand, many people forget about it. So it's described in such a strange way, perhaps, but torsion-free cyclic groups. So all of you passed some algebra course, so everybody knows what cyclic groups are. I mean, there are very few of them. If you additionally add torsion-free, there's only one. Or two, because there's a trivial one in the integers. So that's what is written. Now, what is a little bit less trivial, but yeah, I'm saying that sigma f is f bar. But this is well known. What is sigma f? This would be all groups with the property that the H is in F. So what does it mean? You take any finite subset, you look at this, at the group generated by this subset, cyclic and torsion-free. So isomorphic to the integers. This is what is really, I found it some few days ago that they really have a name, locally cyclic. And the biggest one is the rationals. And you try to extend the group of the rationals by adding some element and generating something in this class. No way, it will always be inside. All torsion-free, all locally cyclic groups are actually images, homomorphic images of subgroups of this one. So all of them are countable. Here you actually have, let's see, the amalgamation property is very easy because you have two embeddings of the integers into itself, they commute with each other. So we put them the other direction and get. This is an easy exercise. Let's skip it. Now, I will quickly show several classical ways of constructing uncountable homogeneous structes. So, Fraisse-Johnson theory. Okay, Fraisse wrote his paper in published in '54 about Fraisse limits. He didn't call them like that. Yeah. Okay. And then, like a little bit here, well, less than 10 years after, Bjarni Jonsson, a logician from Sweden, Scandinavia, not sure. Something like Jonsson Calculus was well-known logician. He was developing similar things for arbitrary cardinalities. And he wrote a series of papers. I think that in the second one he already knew Fraisse's work. And how to say it briefly, Fraisse observed the following thing. You have these axioms. This is actually important. So what do? You build something which can be called a Fraisse sequence. The notion of a Fraisse sequence was by me in 2000 something, but never mind. It's the essence of Fraisse theory in category theory. But here in model theory, you just start with something like, K0, you are adding, but these are all embeddings, inclusion. What you do, you want to realize the amalgamation property. So, for instance, somebody is giving you some embedding, and you have countably many possibilities. So you can enumerate all of them. Using amalgamation, you can simply spend, say, this one. So you are knowing the fact that there are countably many possibilities, you can simply build inductively a chain, tower, or whatever you call it, so that everything is realized. This is this Fraisse sequence, and then you prove by back and forth argument of these things. Yeah? And now, if we have, let's say, good cardinal arithmetic, so for example, as it is written here, CH, continuum hypothesis, which I don't like too much, I prefer ZFC results. But if you have CH, if you look at countable structures, think of graphs, for example, yeah, countable graphs. We have continuum many possibilities already, right? Because, for instance, you have a graph, a countable graph, and you can even continuum many embeddings. If you have an infinite graph and adding one more vertex, yeah? For each subset, you declare that it is connected to this subset. This already gives you continuum math. But if there is no more, exactly continuum. And once you have a countable chain of countable graphs, its union is a countable graph. So you can build this thing by transfinite induction. At limit steps you survive, successor steps you use amalgamation, and you can do it because there are continuum many possibilities, and continuum is Rf1, so from all countable ordinals you obtain something which can be called a Fraser sequence, and then the resulting structure is really as homogeneous as possible, in the sense that every isomorphism between countable substructures extends to automorphism. So it is really a strong homogeneity. It's hard to expect better one. Okay. But as you see, this requires CH. Once you have GCH, then you can do it for other kind. Yeah. Regular. But okay, I don't want to go into details. Yeah, the existence of such a structure is sometimes equivalent to CH. But let's skip this because sometimes it's running. Another thing, ultra powers. Well, here you don't need any cardinal arithmetic. That's another problem. So it goes to some paper of Kissler, the old one. Was actually proving that the ultra power is omega-1 saturated, whatever it means. And you can prove homogeneity. But there are, I'm not sure now if I wrote this, no. If the language is finite, the language of F, and it's relational, and first of all, the ultra power, the age of the ultra power may not be in F anymore. If your language is infinite. For instance, you take graphs, maybe complete graphs with colorings, each edge has a color, maybe with some restrictions. No large monochromatic sets, no? And the number of colors is infinite. It's an infinite relational language, but in the ultra power, for those of you who know, can see that some pairs may have no color. Because the color is green if the set of coordinates where you see the green is in the ultra filter. Maybe you have infinitely many colors appearing green. You lose the property. So the ultra power of any ultra product may be far from your original class. That's the problem. So sometimes homogeneity works, you get a structure of size continuum, but it is kind of restrictive. Now, so I want to make it short. I should not spend much time on this particular thing. There was a general question when you have this U, you take the group of automorphism. When is it universal? In the sense that any structure from sigma F, you have X from sigma F, and you have both X, just that X is always an embedded. It's universality of this group. For many classes, it is universal, but there are some counterexamples. And a general method of proving this kind of universality. This was our motivation. Some old work with Katarzyna Mandrowicz from Novi Sad. But I wrote some very special case of our result. You have a functor, okay, so category theory appears here. But for that, our paper is written in model theory using only the language of category theory, including some extension. Okay, we have a functor. So what does it mean? You have to each structure like X, you assign some bigger structure, adding some one-point extensions perhaps and collect them all. And a natural transformation is like something uniform, going from X to K of X, X, and it commutes with the functor, more or less like this. And suppose that the functor is so good, or maybe you iterate it, and many times, so that K of U is U, up to isomorphism, but some bigger copy of U, okay, bigger copy of the phrasal U. Then, you repeat this functor omega one many times, you have an uncountable homogeneous structure. What is a non-trivial embedding? Not an isomorphism. Okay? An embedding which is not an isomorphism. So you think of it that it is inclusion, means that K of U is strictly bigger. Okay? And then you get, like, you can iterate this functor omega one many times. The natural transformation allows you. If you have something like that, you repeat it again, K squared, K cubed, etc. That limit ordinals will take the union of this so-called chain. So this gives a method, except that nowadays there are at least several Fraser classes that known already that do not have such a functor. This functor is a really strong property. Okay, so I'm going to the main result, more or less. So, well, there is still now the question left. How to construct an uncountable structure which has some nice homogeneity, maybe in some somewhat minimal way, not using ultra powers because perhaps our language is infinite or something, and not using any cardinal arithmetic, not using almost anything. So what we can do? But still, the main question is still left open. So okay, and then just put a name for the moment of all self-embeddings. Okay, so think of your favorite Fraser limit, maybe the radograph. You look at all copies of the radograph inside, yeah? You see embeddings. And this, but yeah, you have to take also abstract versions. And then the composition of two embeddings is an embedding. So this is a model. It's typically uncountable. And it could be trivial. See this example with torsion-free cyclic groups. Yeah, I mean, there's only one embedding of the rationals into itself, the identity. Maybe not the only, but all of them are isomorphisms because you can move one to minus or the minus, for instance. But there is nothing like adding more elements. All of them are automorphisms. And yeah, actually, if this monoid is non-trivial, then we can construct some uncountable structures. Do you agree? One piece of information is needed, perhaps. So, if our monoid is non-trivial, after all, you have some inclusion, which is not, you can always think that it is inclusion, which is not equality, yes? Something like that. Okay. So So I have added at least one more element. And yeah, it is, so for instance, you take, if your favorite phrase class is this one, if you are adding, what is your favorite irrational number?
E.
What?
E.
Oh, E, yes, yes. This is a non-trivial element. This is still isomorphic to the rationals. And so once you have this, you can repeat it first omega many times. And now one thing which you could believe that if you have a chain of structures, all of them isomorphic to the phrase limit, the union is isomorphic to the phrase limit. Instead of homogeneity, you prove the extension property. We have a finite substructure inside the union, so it is captured in one of the pieces. With some extension is captured also in the piece. So it's the extension property, and that's equivalent for countable structures, for phrase limits, not for arbitrary homogeneous structures. Homogeneity is stronger than extension. So, but when we have this, so we can repeat it omega 1 many times. But we obtain a structure of cardinality omega 1. But it may turn out to be rigid instead of homogeneous. Maybe some of you heard of rigid subsets of the real line of cardinality R1. They sometimes exist. Cardinality continuum definitely, and you don't need any forcing, but so this omega 1, the union of this omega 1 chain can actually lose all automorphisms. This sometimes happens. Easy to do it by forcing. There's Janet Costana, maybe some of you know him, was my PhD student, who has results like that. Okay, on the other hand, if the language is finite and relational, and then this is non-trivial. Okay, I thought actually this claim is false because you need to know that F contains arbitrarily large finite structures. The Fano claim. So F say finite, but the language is finite, but F should be really non-trivial. Infinite phrasal class, let's say. Infinitely many isomorphic types. And actually, one of the reasons is that you take the phrase limit and there is amalgamation property still holds for infinite structures. That's why you can do it, and since the language is relational, you don't have this problem like with algebra, but uniquely finite elements. Okay, here is a stupid example, so maybe we should skip it. This is a relational class, so okay, very quickly, you have a set, and each point has a color, but each point has a different color. The colors are natural numbers. So formally, it's a phrase class, amalgamation property holds, but you have to glue the points sometimes. And infinite set where all the colors appear, this is a maximal structure. You cannot do anything with that. So this can happen, but this is kind of stupid. Now the result, I hope to have some time to explain a little bit of details in a few minutes, yeah? There is already 6:01, so but look, I have this question is still open. Let me check if I have anything more. Okay. There's something about anti-metric spaces. Everybody knows metric spaces. So anti-metric is like the triangle inequality, always fails. So you can imagine what it is. This is an example of a relational class such that infinite structures fail the amalgamation property. This was, I think, all. So let me go back to this result. The positive result is that if the language is relational and finite, the amalgamation survives at infinite structures. In the proof, something like Koenig's lemma for tree is used. It's not obvious, but it is easy to prove. So let's not talk about it. Now there is this like algebraic result that if the monoid of embeddings has some reasonable properties, so many Fraser classes do have this, and then there is a way of constructing this uncountable structure. Now, what are these properties? You take all the automorphisms of U, which typically there are many, continuum many. The automorphism group is a Polish group after all. You know it probably from last week. And so a Polish group is either countable or has cardinality continuum. Yeah? Analytic in particular. So very often the automorphism group is already of size continuum. But we would like to add at least one non-trivial embedding, maybe all of them, but maybe at least one. And suppose we are able to prove the amalgamation property. As usual amalgamation property, except that you have embeddings from U to U. And you have a single embedding and you have the same embedding, then you amalgamate by identities. But if this is composed by an automorphism on this side, then you don't know what to do. So this is a non-trivial assumption. And if you can amalgamate it in sigma f, then this is not a Fraser limit, but the Fraser limit is universal, so you can continue that amalgamation with the model. Okay? So suppose that you can do it. So as I said, this is already a weak assumption. Then what we can do? Now we are using abstract Fraser theory. Okay, so for set theories, I would say the following: take a countable elementary submodel of something which knows this monoid, but you can also take elementary submonoid of this, with still no logic. Okay, closing of argument. You take a countable submonoid which knows enough. Elementary is probably the best is to have the intersection with a countable elementary submodel of some part of set theory. But what do we really need to know? It needs to know that U is a homogeneous structure. U has only countably many partial isomorphisms of this sort. All of these are finitely generated. So there are countably many possibilities. Each of them extend to an automorphism. So M0 would actually know a countable subgroup of the automorphism group, which will witness homogeneity. This is possible. And then M0 should be closed under amalgamations. So M0 is a Fraser category. A monoid which is a Fraser category. Countable. So we build a Fraser sequence, starting from U, finishing with U. Sorry, the colimit will be U. The Fraser sequence is an infinite sequence. Now, we take any automorphism which is known by this, by back and forth argument, it extends the automorphism of U. It's something like extending automorphisms. So now, suppose we captured, we take a finite isomorphism or finitely generated isomorphism here in this thing. We know that it extends to an automorphism which is known by this guy. We can proceed by going to an automorphism here. We collect all these automorphisms which appear here, and we repeat this procedure. If you want to do it in one step, you take so-called omega-1 chain of countable elementary submodels of something, yeah, m alpha plus 1 has m alpha as an element. So this is standard thinking set theory. And like this way we can build an omega-1 chain, and the resulting structure, this W, will really be homogeneous because every finitely generated isomorphism is captured at some step. Then it's extended to an automorphism of some group like the one known by this BF alpha, okay? And then inductively you extend for it. So somehow this is very model theoretical algebraic, very standard, yeah? There's no category here. But the idea which is behind, yeah, is like you are using the phrase sequence in some strange setting, yeah. Okay, so this is how it works. Jill, I found this result like preparing this talk. Yeah? I wanted to have some weaker result originally, but we discussed it with Adam, so it seems that everything works. Our third co-author still doesn't know it. So, thank you in that case. And yeah, I showed it in the last part. Yeah, is the proof of the claim requires somewhere, but it's not difficult. Okay, so simply. Thank you.
Thank you.
Thank you. Questions, comments? Well, I've got a technical question. Can we put your slides on our webpage?
Yeah, of course, except that maybe a better version with your poses. Yeah? Because if somebody looks at it, it's better with around smaller number of slides. Yeah? So I have another one.
And similar question, how about the recording? Can we put the link to the recording on the webpage?
Yeah.
That's okay. Okay.
Okay, so thank you again.
Thank you.
To start.
I'm trying to do this. Okay.